Hi there! Remember from the previous video that we investigated how a proportional controller can control the water level of a tank inside the factory I/O software. A proportional controller is the simplest form of PID controllers. In this video, we are going to take a look at the performance of PI and PID controllers. As it was mentioned already, a PID controller continuously receives an error value, which is the difference between a desired set point and a measured process variable, and applies a correction based on the proportional, integral, and derivative terms. In the previous video, we investigated the performance of the proportional term. As you can see, we can add the integral and derivative terms to the controller in a parallel form. Let's check the performance of the controller when it is only using the proportional and integral terms. As in case of the water tank, let's assume that set point value is 110 centimeters and the current water level or PV is equal to 90 centimeters. Naturally, the error value E0 is 20 centimeters. As you can see, the output of my PI controller consists of only two sections. In the beginning, because elapsed time is small, the output of the integral section is close to zero, and the output of the proportional section is not zero. So the proportional section plays the main role to determine the output of the controller. A non-zero number causes the controller to open the inlet valve. For example, let's assume the PV value has reached 100 centimeters and therefore the E1 is equal to 10. Notice that as the error value decreases, or 10 versus 20, the output of the proportional section is also decreased, but with the passage of the time, the output of the integral section will no longer be equal to zero. Up until now, the error values are positive, so the output of the two terms is positive. In consequence, the inlet valve will be open to raise the water level and to decrease the error value until the error value to reach zero. Notice that when E3 is equal to 0, the output of the P term is equal to 0, but the output of the integral part is not equal to 0 anymore. In previous video, we saw an example that sometimes in order to keep the error value equal to 0, the output of the controller should be a non-zero number. In this video, the integral term can use the previous errors to compute a non-zero output value. This feature can help to keep the water level at desired SP value, but it has a weakness in the beginning. Now, the previous error values are larger numbers, and when the integral term sums them to determine its output, it will generate a large output value to open the inlet valve as well. So it causes the PV value to pass from the SP value. For example, the PV value can reach 112 centimeters, which is greater than the SP value. But when the errors are negative, the controller tries to close the inlet valve to decrease the water level and return the PV value to the SP value, which is equal to 110 centimeters. Let's assume that this black line is the indicator of the desired water level and the red curve is the indicator of the water level inside the tank. Notice that by adding the integral term to the proportional controller, it takes a longer time to bring the water level to the desired level, but on the other side, it can bring the water level to the SP value and keep it at the SP level with a very minor error. Pay attention that at the beginning of the controlling process and when the error values are high and the elapsed time is small, the proportional section plays the main role to determine the output of the controller. But with the passage of time and the reduction of error values, the output of the integrator term plays the main role to determine the output of the PI controller. Also, pay attention that although the integrator part of the PI controller is able to reduce the weakness of the P controller, which was investigated in the previous video, but it introduces a new problem to the performance of the PI controller, and that is the presence of fluctuation at the beginning of the red curve, and as a result it takes more time for the water level to reach the desired level. In general, in some applications, the weakness of the integrator part can be ignored, but if we want to minimize the presence of these fluctuations, we can add the derivative term to the controller. Try to describe the function of the derivative part of the PID controller for yourself, just like my explanation for the integral part. Pay attention, depending on the system's conditions and requirements, we can increase or decrease the effect of each section of a PID controller by changing the related coefficient. In this diagram, you can generally see the effect of each coefficient of PID controllers to bring a process value to its desired setpoint value. Alright, like the previous video, let's check the performance of our PI controller using the water tank system. Remember from the previous video that we disabled the integral term of the function block 41, but in this video we need it. So let's remove this input. Note that the performance of a PID controller can also be defined by this mathematical formula, and according to that, I set a time of 5 seconds for the TI coefficient related to the integral part. Now let's connect an address from the memory to the ER output to see the error value. Now let's download the designed PI controller to control the water level. Well, here is a problem. My PI controller performs like the proportional controller as we observed in the previous video. I checked my program and I found the reason for my problem. Note that, as I mentioned in the previous video, when the FB41 is used for the first time, by default its integral term is enabled. But I used my FB41 in the previous video and I disabled its integral part, and now I need to activate it by setting it to 1. Also, I prefer to change gain and TI coefficient to 2 and 10 seconds respectively. Okay, my PI controller has started its work. Pay attention that the outlet valve of the tank is permanently open and the controller only controls the inlet valve. As you can see, by using the integral term, my PI controller can raise the water level to the desired level and keep it at the level with a very small error. Again, let's change the desired water level to observe how the PI controller performs. If you pay attention to the changes in the water level or the sign of error values, you will notice that before the water level is fixed at a desired level, it goes up and down around the desired level, and then it stabilizes at the desired level. As I explained earlier, the reason for these fluctuations is the use of integral term of the PI controller. Again, let's change the desired water level. As you can see, the performance of the PI controller to control the water level is satisfactory. We can use this PI controller in many industrial applications. But if we need to have a faster controller, according to the video, we can add the derivative section to the controller. To activate the derivative section, we need to activate the diesel parameter and assign a value for the TD coefficient. Now let's change the desired water level and test the performance of the PID controller. As you can see, the PID controller can raise the water level to the desired level and keep it at the desired level with a very small error. I hope you, by watching the last 4 videos related to different methods of designing controllers, you have become familiar with the strengths and weaknesses of each of them, and you can design and use the best controller according to your needs if needed. Thanks for watching this video. See you in the next one.